Hello everyone, this is Bhumi Thakkar. I will be explaining you regression. So what is regression? Regression is a statistical modeling procedure. Basically, it's a procedure for which estimates the relationship between the variables. That what is the relationship among the variables. The main focus is on estimating the relationship between a dependent variable and one or more independent variable. Uh, the more specifically what we can say is that by regression we can understand how the change in one of the independent variable value of one of the independent variable can affect the dependent variable while the other independent variables are held fixed. Regression is like very basic. When you start learning predictive modeling, the first step you do is learn regression. Now I just want to give a short information about predictive modeling. Predictive modeling is a process of building, evaluating and validating a model which helps us to predict the output. So the first step is regression, as I said. um, so in simple terms, I would like to say that it is a function that predicts a real number. Like we can predict age, weight, distance, temperature, income, or sales. It can also this all thing can be predicted by regression. The one example I would say that we can predict the children's height if we have the data about its age, weight, and other factors. The So regression tasks, what in regression tasks we what we do is we first need to have a data set in which we know the values of the target variable, and hence on that data set we can build a model, and that model further can be used to determine the the future tuples. If we give like in our children heights example, what we can do is we can have a data set in which data about a few children, age, weight, etc. are given, and also their height is given, which is our target variable. And hence each data for each child would constitute a case. So what is actually done in building like this training process? The data set we use is used to build a model. That is, we actually identify the relationship about among the variables. That is how our dependent variable is related to our independent variables, and that relationship which we identify in our training process, that is in the building model process, we can use it to determine the future tuples. If such information about the child is given and we are required to predict the height, so if we are building a model, right, so we need to test it. So we can do it by computing various statistics. That is, we can measure the difference between the predicted values and the expected values, and we will get error. From this we will get an error, and by error we can know, like, the lesser the error, the more good is the model. Now, if we talk about regression, the first thing we have to learn about it, that one of the type is linear regression. Linear regression is used when we have to identify the degree of relationship between two or more variables. So in linear regression also we have two types, that is simple linear regression and complex linear regression. Simple linear regression is a regression in which there is only one dependent variable and one independent variable, while the complex, that is the multiple regression, is when there is more than one independent variable. So how the linear regression is used for regression analysis? It actually tries to fit a single line through a scatter plot. This is a scatter plot. If we don't consider a line over here, we will get dots where we have two axes, x and y. this x is actually our input variable, right? If we consider simple linear regression, we have a dependent and independent variables. So x will be our independent variable which we actually will input, and y is our dependent variable which we actually want to predict. So the simplest form of regression can be defined by the formula y is equal to ax plus b, where y is our target variable, a is the slope of the line which is shown in this graph, b is the y-intercept the line makes on that graph. So we can use this formula to determine. This is the figure, x-axis, y-axis, and these are our data points, and a line is drawn through them, which how it is decided that which line is best, I will show you later. For now, keep this in mind at the simple concept. As shown in the figure, there is a black line passes to the data points. There are three data points: 0, 0, 4, 8 and 30, 60. Here's like if we have a question like find the equation that describes this line, that is we have to find the relation between y and x. So we'll first write y is equal to a into x plus b. So by looking over here, we know that the slope of the line is determined by y2 minus y1 upon x2 minus x1. So here if we consider the points 0, 0 and 4, 8, the 8 minus 0 upon 4 minus 0, that is 2. Okay, so our slope of the line is 2, hence a is equal to 2, and this line doesn't make any intercept with the y-intercept, so the value of b is 0. So our equation becomes y is equal to 2 into x plus 0, and which is actually y is 2 into x. Hence we get the relationship between these two variables, where x is our independent variable and y is our dependent variable. This equation is called as linear regression equation. A is known as I told you, a is the slope, b is the intercept. I already shown you that. Now the question arises is like there can be many lines that can be drawn to this point. Why only this line, right? Why this? So we actually have to find the best fit line, or the value of and according to that we have to determine the relationship. So the next point will be how to find the best regression line. There may be multiple lines, so which is the best? How to do that? We discussed about that the regression line establishes a relationship between the independent and dependent variable. So that line should be a best fit, as I already told you. So what we do is the line which we consider as a best fit should have a minimum difference between the actual and predicted value of y. That is a target variable value, predicted target value, but should not have much difference with our actual variable. So we have to see, this is the graph x and y. Over here you can see a line, and you can see that there is a predicted value and actual value, and in between that is there is an error. So we want to find such a line where the error is the minimum. So there are three methods for that: sum of all errors, sum of absolute value of all errors, and sum of square of all errors. So what I will do here is I want to know that which among the three is the best. So here's a graph. I have three lines over here: y is equal to 2.3 x plus 4, y is equal to 1.8 x plus 3.5, and y is equal to 2x plus 8. And we have to show that which one is the better, and what I have done is, there is a table. We have these are x and y are the coordinates of our points. There are three lines, so I have made three columns for each one. Now as I said, there are three methods: sum of all errors, sum of absolute value of errors. So I have made three columns for all of them: sum of all errors. So what I have done is, by using an equation, equation of the line y is equal to 2.3x plus 4, I have found out the value of y, which comes out to be minus 3.4. Then similarly, according to the sum of all error method, which is in the blue tuple, right, I have calculated the value of y using an equation y is equal to 1.8x plus 3.5. And similarly for the third line, that is y is equal to 2x plus 8, I have an error, that is minus 5. Okay. Now we will use a second method, which is sum of absolute value of all errors. So whatever error I have got in the blue tuple, that is minus 3.4, 1.1 and minus 5, I will do an absolute value of it, that is the all negative sign will be cancelled out, and we will get 3.4, 1.1 and 5. This comes to okay. And the third one, for the first tuple, what is we have that sum of square of all errors, right? So what actually is that we have taken the squares of our error, that is 3.4 square is 11.56, 1.1 square is 1.24 and 5 square is 25. Now we have similarly we have calculated the error according to the three methods for the all the data points, and then we have summed it, okay, because the methods are that only, sum of all errors, sum of absolute value of errors and sum of square of all errors. So basically we have summed it. So minus 0.6, 47.9, minus 36, these are the sum of all errors for the three lines. And similarly we have for other two. The important observation here we have to make is minus the first method, that is sum of all errors, is not efficient here, because here the while we sum all the errors, the negative and positive cancel out each other, so we do not exactly get the error value. So hence the first method we cannot use. The second method, however, is efficient, that is we have taken the mod and then sum of the errors. And third method is also good, that where we have taken the sum of the squares of the errors. However, which one of those two are better, which one of the two are better? So for that we see the error value, that is see the purple tuples and the pink tuples and the final sum. We can see that the difference between the error value, sum of errors value, or between if we consider the second method, there is a little difference between the two lines, hence it will be difficult to decide which line will be the best fit. However, if we take the third method, there is a tremendous amount of difference between the sum value, and hence we can easily decide that which line is the best fit. So the preferable method is sum of square of all the errors, which is our third method. This is all the observations. This slide contains the three observations I just told you. Now yes, we have prepared the model, so but there should be something like to evaluate it. So performance evaluation metrics come into picture. Now you can say that okay fine, let's use sum of square of all errors only as the performance metrics, but it cannot be used because as you can see here, you can see a table, two table, in which in one table there are all the data points are included, while in the second table few of the data points are discarded. And when you actually calculate the sum of square of all errors, we come to know that in the first table the error value is 93.99, while the second table is 76.19. So we can see that when we discard the points, the error has reduced a lot, hence the sum of square errors is highly sensitive to data points. But when you see the graph is almost similar, that is the line that we use is almost similar, but still the error sum of error is quite different. So using sum of squared errors as a performance evaluation is not a good idea. So now what, there should be something to do that. So in that, now there comes an R square matrix. The R square matrix is one of the most used metric to evaluate the performance of linear regression. So it actually measures that how much the change in output variable is explained by the change in the input variable. If we change the independent variable by some quantity, so how much of what it how in what to what extent it changes the dependent variable, that is what it measures. The whatever value you get by R square is between 0 and 1. The 0 indicates that the model explains nil variability in the response data around its mean, and 1 indicates that the model explains full variability in the response data around its mean. So in layman words, I would say that the higher the value of R square, the more robust is your model, because 0 indicates that the change in the change in the independent variable has the very like nil effect on the output variable. So that is not desirable, right? Because we are actually trying to find the relationship between them. So, and 1 indicates that it has a full effect, like the change in the dependent variable has a full effect. So 1 is desirable. So we can say that the higher the R square, more robust will be the model. Um, okay, here we have a table. Like we want to see that the situation we faced situation we faced in SSE, that is squared sum of squared error. The same situation should not exist in R square, right? Because then the very point of using the R square is like a complete bad idea. So we have done the same thing, like that is we have used R square and we have predicted the value that in first table, while when we consider all the data points, while in the second table some of the values are discarded, and here we see that there is a little change in the error value, that is R square value in the first table is 0.83, while the R square value in the second table is 0.78. So hardly there is a change of 0.05, and which is like very less. So the number of data points has like the R square is less sensitive to the number of data points, and hence we can use R square. Now there is one disadvantage of R square, that is the R square can only be increased if the predictors are added to the regression model, that is if more and more independent variables are added. But just adding more and more independent variables won't serve the purpose, because the addition, that is the increase in the increase is artificial if those independent variables, that is our predictors, are not actually improving the model's speed, that is they are not actually contributing to the relation that affecting the our dependent variable. So in that case we use an adjusted R squared, which is one of the metrics. So what actually is adjusted R square? It is nothing but it determines the change of R square that adjusts the number of terms in a model. Adjusted R square calculates the proportion of the variation in the dependent variable accounted by the experimental variables. That is, it actually determines that how much proportion of variation is actually seen in our dependent variable when we change our experimental variable. Adjusted R should always be used with models with more than one predicted variable, because the sole purpose of using the adjusted R square is that as we have seen, the very sole purpose of using the adjusted R square is that we have to increase the value of R square, right? So this is adjusted R square. The formula of R square adjusted is 1 minus, that you are seeing on the screen, where R square is a sample R square, that and the P is number of predictors, that is the P is number of independent variables, N is the total sample size, that is total number of tuples in our data sets. This is the formula. Now one more regression is multivariate regression, and as the name implies, it actually is a technique that estimates a single regression model with more than one outcome variable. Now you may get confused between multivariate regression and multiple regression. As I told you earlier, that multiple regression is used when there is one dependent variable but more than one independent variable, while a multivariate regression is used when there are more than one outcome variable. So there is a lot of difference between them. You will understand it more with an example. So I am giving you three examples. Example one is, if a researcher has collected a data on three psychological variables, four academic variable, and the type of educational program the student is in for 600 high school students. That is, he has actually collected the three different type of data, and if she is interested, like, to find the relationship among this different type of variables, that is, if she wants to find how the set of psychological variables related to the academic variable and the type of program the student is in, then we will go for multivariate regression. The other two examples are similar. The Suppose a doctor has collected a data on the cholesterol, blood pressure, and weight of a patient, and also about its eating habits. And if she wants to determine that what is the relationship between these three measures, that is cholesterol, blood pressure, and weight, and that of the eating habits, she has to go for multivariate regression. Similarly, the third example, you can read it. It is based on the same thing, that you have more than one outcome variable. So that is regression. So regression is quite simple, and I hope you have I have explained it better. So thank you.